Hello, in this video, I will go over the different techniques of solving improper integrals. Um, when the boundary is negative, infinity, and pos infinity. I will also go over the steps when f is discontinuous. So this is calculus 2, and we are going over improper integrals. So improper integrals, by the definition of fundamental theorem calculus, a definite integral requires that the intervals from a to b be finite, and then the function be f to be continuous. So that is when it's uh, proper. But so what happens when one or both of the limits of the integration are infinite? So boundary, yeah. So if your boundary is like from negative infinity to positive infinity, uh, or if the f is undefined, discontinuous at one or more points of the interval from a to b, you have an improper integral. So let's go over the rules. Okay, so first rule for improper integrals. Sorry. Okay, so yeah, the rules. So rule one, if your integral looks anything like this, the lower boundary a is an actual real number and your upper boundary is infinity of f of x d of x, you're going to somehow convert it to, or you're going to rewrite it as the limit as b goes to infinity from a to b of f of x d of x. Uh, you'll see when we do an example. And then if your rule two, if your integral looks anything like this, where the lower boundary is a negative infinity and the upper boundary is a real number, f of x d of x equals the limit, then you're going to rewrite it as the limit as a goes to negative infinity from a to b of f of x d of x. Okay, I'll show an example. Rule three, if your integral looks anything like this, where the lower boundary is negative infinity and the upper boundary is positive infinity of f of x d of x, what you're going to have to do is write it out as two separate integrals. Um, your first integral will be from negative infinity to c, or a real number, f of x d of x plus this same real number below to infinity of f of x d of x, and that's going to equal to this. The limit as a approaches infinity, uh, bracket from negative a to c of f of x d of x plus integrals from c to a of f of x d of x. So just write it down. I will explain. Where c is all real numbers. If the limit exists, then the improper integral converges to that value. If the limit does not exist, then the improper integral diverges. Okay, let's do example one. So we have the integrals from 1 to infinity from the rational function 1 over x d of x. So if you want to kind of draw it, that's fine. If you were to graph one, what does y equals 1 over x look like? It's a rational function that looks like this. It has a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And on the right behavior, it looks like this. on the left, it looks something like this. Okay, so what you got to do, what we're trying to do is going from 1 to infinity. So we're trying to find the area from this area. Okay, so it's from 1 to infinity. So I believe that's rule 1. Yeah, so our lower boundary is a real number. Our upper boundary is infinity. So it is rule 1. So what I'm going to do is rewrite it as the limit as b goes to infinity from the integral from 1 to b, right? So this is rule 1. Our rule, if your integral goes from 1 to a real number to infinity, you're going to rewrite it as this: limit as b goes to infinity from 1 to b of 1x dx. Now, you know how to take the integral of 1 over x, right? The integral of 1 over x d of x is just ln of absolute value of x. So that's the first thing I need to do. I need to figure out what's the integral of 1 over x. Okay. So now what we're going to do is, once we know the integral of 1 over x, I'm going to rewrite it as the limit as b goes to infinity of ln of absolute value of x, because the integral of 1 over x is ln of absolute value of x, from 1 to b. And then you can write it out as limit as b goes to infinity. And then you just apply fundamental theorem. You do the upper minus the lower. So ln of absolute value b minus the ln of absolute value 1, right? Just simple fundamental theorem. Okay. And then remember, our limit is going from b to infinity. So this is going to be so okay, so we're gonna write it out as two separate integrals if we need. Wait, yes. So it's gonna be limit. So I'm gonna write out as two separate integrals where the limit as b goes to infinity. Okay. Then then we just plug in our b to infinity. So what is the ln? So it's going to be ln of absolute value of infinity minus uh, ln of 1 is, so it's going to be the limit as b goes to infinity. Right, so the ln of 1, if you put that in the calculator, that's 0. So as b goes to infinity, the y value or the limit is still infinity, 0. This is going to be 0. What is the ln of absolute value of infinity? Believe it or not, it is infinity. Minus 0. What is infinity minus 0? It is infinity. So if you have infinity or negative infinity, you could also say it also diverges. You're probably thinking, how do I know that the limit of ln of the limit as ln of absolute value, the limit as b goes to infinity of ln of infinity is infinity? Well, if you recall, what is the graph of y equals of a natural log? It looks something like this. See, as b goes to infinity, as b goes to infinity, what happens to the y value? It slowly decreases out to infinity. Okay. Okay, let's do example two. So example two, we have the integrals from 0 to infinity of 1 over e to the x d of x. So that's still part of rule one. We have our lower boundary is a real number and our upper boundary is infinity. So yeah, it's rule one. So we're going to rewrite it as limit as b goes to infinity, integrals 0 to b of 1 over ex dx. And what do I do? I 1 over e to, I'm going to rewrite this as a negative power. So I'm going to say limit from 0 to b. And then I'm just going to rewrite 1 over e to the x as a negative power, e to the negative x dx. Now, I think this is more doable. What is the integral of e to the negative x d of x? It's basically itself divided by the derivative of negative x. So what's the derivative of negative x? Yes, it is negative 1. So yeah, that is going to be negative e to the negative x. Or you could have just do use substitution, you'll get the same answer. So the integral of e to the negative x is basically itself divided by the derivative of the power. Okay, since we know that, we can rewrite it as the limit as b goes to infinity. And we could just apply fundamentals. So the integral of e to the negative x was negative e to the negative x. And then you could just apply your fundamental. Our lower boundary is 0 and our upper boundary is b. So this is going to be the limit as b goes to infinity from negative e, and then apply the upper boundary minus lower. So it's negative e, and then it's negative, and then your upper boundary is b, minus parentheses negative e, and then it's going to be minus 0. Okay, so this is going to be the limit as b goes to infinity, negative e to the negative e raised to the negative b. Over here, two negatives become a positive. E to the 0 is 1. Or actually, let's just rewrite it as two separate intervals. So yeah, be careful. So we're going to write it as two separate intervals. So we're going to say limit as b goes to infinity from negative e to the negative b minus, because there's a minus right here, minus the limit as b goes to infinity of negative e to the 0. Okay, so we're going to rewrite it as limit as b goes to infinity. How can I write negative e to the negative e raised to the negative e? You can write that as a positive power. So that'd be negative 1 over e to the b minus the limit as b goes to infinity. And then what's e to the 0? Positive 1. And then you have this minus, so that's negative 1. Okay, now you can plug in your b for infinity. So this is going to be negative 1 over e raised to the infinity minus uh, what's the limit? What is the limit as b approaches infinity of the function y equals -1? It's still going to be -1. Okay, so uh, what is this? What is -1 over e to infinity? That is, it's basically negative over a very large number. 1 over infinity is 0, 0. And then over here you have two negatives becomes a positive. So 0 plus 1 is 1. And it converges. Not, yeah, it converges because it's a real number. Let's move on to example 3. So example 3 says we have to find the limit from 1 to infinity of 1 over x squared plus 1 d of x. So what is our rule? We have a lower boundary of 1, which is a real number, and an upper boundary of positive infinity. So I still believe that's rule 1. So you're going to write it out as the limit as b goes to infinity from the integrals 1 to b, we change infinity to b, 1 over x squared plus 1 dx. And we know what is the integral of 1 over x squared plus 1 dx? That's a special one. Uh, that's this rule 1 over ax squared plus b squared. So our a is 1. Yeah, our a is 1 because there's no number here, just a 1. And our b is also 1. What number squared gives you 1? 1. So it's going to be 1 over ab times tan inverse of ax over b. That means the integral of 1 over x squared plus 1 is going to be 1 over ab. So 1 times 1 is 1 tan inverse of ax, which is 1x over 1. So really it's just tan inverse of x. Okay, so we need that. Okay. So we can rewrite it as the limit as b goes to infinity of tan inverse of x, and then our lower boundary is 1 and our upper boundary is b. So now you can apply the fundamentals, so it would be the limit and apply your upper minus lower, so it's going to be tan inverse of b minus tan inverse of 1. So this is going to be the limit as b goes to infinity. And then we'll just write out as two separate intervals. So it's going to be tan inverse of b minus the limit as b goes to infinity of tan inverse of 1. So we got to kind of, in order to, let's see. Let's kind of look over the graphs. Before we find the limit, let's kind of review what the graph of tan of x and graph of tan inverse graph looks like. So if you recall, the graph of tan of x looks like this. You have a vertical asymptote at pi over 2, negative pi over 2, and then the other graph is what does the tan inverse graph look like? It's the reciprocal of this, so it's going to be you have a horizontal asymptote at pi over 2, and another horizontal asymptote at negative pi over 2. Okay, it would look something like this. Okay, so that's going to be helpful when we find the limits. Okay, so let's move on. So it's going to be the limit as b approaches infinity of tan inverse of b minus the limit as b approaches infinity of pi over 4. If you put tan inverse of 1, what is that tan inverse of 1? So what degree in radians gives you a tangent of positive 1, pi over 4? Okay, so now you just plug in your b for infinity. So over here, this would be tan inverse of infinity and minus, as the limit approaches b to infinity of the graph pi over 4, it's still going to spit out pi over 4. And then if you look at this graph, the tan inverse graph, as b goes to infinity, uh, it looks like it stops at pi over 2. So this is going to be pi over 2 minus pi over 4. And if you find LCD, this is 2. It's 2. 2 pi minus 1 pi is 1 pi, so that would be pi over 4. Okay, so that's your final answer. Let's move on to example 4. Okay, so example 4, we have the integrals from a negative infinity to 0 of sine of x d of x. So what rule is that? Our lower limit is a negative infinity, and our upper limit is a real number 0. What rule is that? That is rule 2, right? Our lower boundary is from negative infinity, and our upper boundary is 0. So how we're going to rewrite this as the limit as a approaches negative infinity. And then we're going to rewrite the boundaries from a to 0 of sine of x d of x. Okay, so first I would first figure out what is the integral of sine of x. So the integral of sine of x is negative cosine of x. So this is going to be the limit as a approaches negative infinity from negative cosine of x from a to 0. Okay, and then you just apply. You write it out two separate integrals using fundamentals. So it's going to be the limit as a approaches negative infinity. Apply the upper minus the lower, so minus cosine of 0 minus the limit as a approaches negative infinity of negative cosine of a. Okay. Then do some algebra. So what is the cosine of 0? It is 1, and then there's a minus, so it's -1. So you can rewrite this part as the limit as a goes to negative infinity. So we said that the cosine of 0 is +1, but then you have this minus, so it's going to be -1 minus, and then I guess this stays the same. If you're curious, before we figure out this part, let's kind of review what a cosine graph looks like. The y equals cosine of x looks like this. It starts at the max, like this, and then go down like this, like that. So this is a typical cosine of x graph. Okay, so let's figure out. So what is the limit as a approaches negative infinity of -1? It doesn't matter what the x value is, it's still going to spit out -1 minus, what is so if you plug in this is going to be negative cosine, and then you replace a with negative infinity. So this is what y equals cosine of x graph looks like. And then what does a y equals negative cosine x graph looks like? It's just the reciprocal, so it would look something like this. Instead of a max, you have a minimum, so this is going to be right here. Okay. So it's going to be -1, and then as the limit as a approaches negative infinity of what is the cosine of negative infinity, or the negative cosine of negative infinity? It actually oscillates. It goes so if you look at the negative cosine graph right here, it kind of oscillates. It goes from negative infinity to positive infinity. So that would be undefined. So this is undefined. So yeah, what is -1 minus an undefined? It is undefined. So it's going to be divergence. Okay, let's move on to 5. Okay, let's move example 5. So our integral is from negative, lower boundary is from negative infinity to 0, and then it's the integral from x times e to the negative 2x dx. So what rule is this? Our lower boundary is negative infinity, and our upper boundary is 0. So that would still be rule 2, right? Our lower boundary is from negative infinity, and our upper boundary is a real number 0. So we're going to rewrite this problem as the limit as a approaches negative infinity from a to 0 of x e to the negative 2x dx. Okay, so what is the integral of x e? What is the integral of x times e to the negative 2x dx? Yeah, we kind of have to do some integration by parts, right? What's the integral from x times e to the negative 2x dx? So you have to use what's called the integration by parts. Here's the integration by parts. It's uv minus the integral of v du. So what would be my u? My u would be x. My du, the derivative of x is 1. My dv is the leftover, so our leftover is e to the negative 2x dx. And my v is going to be the integral of e to the negative 2x dx. Okay. Oh, and then what is the integral dx dx? Yeah, what's the integral of e to the negative 2x? That is itself divided by the derivative of the power, which is negative 2. So I'm just focusing on the integral of this. I'm not doing my limits yet. So it's going to be uv minus v du. So it's going to be x times e to the negative 2x minus the integral of v du. So my v is yeah, so we said that the integral of v is this, or you could think of it as negative 1/2 e to the negative 2x. So you have a constant, so you could say minus 1/2 e to the negative 2x dx. Okay, and then we know that two negatives becomes a positive, so that is going to be oh, my bad, my mistake. It's uv minus vdu. So hold on, let's finish this. So if v is negative 1/2 e to the negative 2x, um, so yeah, this is our v, so it's going to be u, which is x. V is negative 1/2 e to the negative 2x minus the integral v du, so it's minus a minus 1/2 e to the negative 2x. What's the integral of e to the negative 2x? That is itself divided by the derivative of negative 2x, which is negative 2. Keep in mind that you also have this positive 1/2. So what's 1/2 times negative 2? That's going to be negative 1/4. e to the negative 2x. So just the integral of x e to the integral of x e raised to the negative 2x dx is going to be this. It is going to be x times negative 1/2. X times negative 1/2 e to the negative 2x is negative 1/2 x e to the negative 2x minus VDU, which we did all this work just to figure out it's negative 1/4 e to the negative 2x. So now we can rewrite this problem as the limit as a goes to negative infinity of negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x. And our lower boundary is from a and our upper boundary is from 0. Right, we change the boundaries, that's how it is. Okay. So now we could just apply the fundamental theorem. So it's going to be the limit as a approaches negative infinity. And then do the upper minus the lower. So it's going to be, let's see, negative 1/2 times 0 e, and then negative 2 times 0 is 0, minus 1/4 e, and then negative 2 times 0 is 0, minus bracket, and then apply the lower boundary. So it's going to be negative 1/2 a e. Negative 2 times a is negative 2a, minus 1/4 e. And then negative 2 times a is negative 2a. Okay, so this is going to be the limit as a approaches negative infinity. And let's see, e to the 0 is 1 times by 0 is, e to the 0 is 1 times by 0. So that's 0 minus e to the 0 is 1 times by negative 1/4 is negative 1/4 minus parentheses. And then remember a is going to infinity. So it's like saying minus limit as a approaches negative infinity, not positive infinity. So that's going to be negative 1/2. And wherever you see an a, replace it with negative infinity. So this is negative 1/2 times by negative infinity, e, and then negative 2 times negative infinity, minus 1/4 e, negative 2 to negative infinity. Okay, clean this up a bit. So 0 minus 1/4 is negative 1/4, minus over here, this is going to be negative times a negative, so it's minus bracket. Negative times a negative is positive, so that's going to be 1/2 infinity e, and then negative 2 times negative infinity is positive infinity, minus 1/4 e, and then negative 2 times negative infinity is positive infinity. Okay. So this is going to be negative 1/4 minus e to the infinity. E raised to a very large number is going to be that very large number times it by another infinity, so that's infinity. Minus e to the infinity minus 1/4 is infinity. Oh, no, this is going to be times. So infinity times infinity is infinity. And then you have this minus, and then you have this negative 1/4. What's negative 1/4 minus infinity, or negative 1/4 and a negative infinity is negative infinity, and that means it diverges. Okay, so let's move on to example 6. Okay, so example 6 says we have to find the integrals from 1 to infinity of parentheses 1 minus x times e raised to the negative x of d of x. How will we do this? What's the rule? We have a real number and then our upper boundary is infinity. So is that rule 1, 2, or 3? Isn't that's rule 1 because we're going our lower boundary is a real number and our upper boundary is infinity. And then how do you take what is this? How do you take the integral of parentheses 1 minus x e to the negative x dx? So just try it out. Shall we use u substitution? No, that won't work. What if I FOIL out this e to the negative x? Will that even help? Maybe. Let's FOIL that out. What's e to the negative x times 1? That's e to the negative x. And then what's e to the negative x times negative x? That is negative x e to the negative x dx. And then what we could do is just take the integral of each term. So this one's not too bad. This one, we might have to do some integration by parts, right? So let's write it out as two separate integrals. So the integral from e to the negative x dx minus the integral of x e to the negative x dx. So right here, this is easy. What's the integral of e to the negative x dx? It's basically itself divided by the derivative of the power. So what's the derivative of negative x? Negative 1. Okay. Okay, now let's do this one. So unfortunately, this is integration by parts. Yeah, integration by parts. So UV, it's UV minus VDU. So my U is X, my DU is 1, my DV is the leftover e to the negative x dx, and then my v, it's basically the integral of this. So what's the integral of e to the negative x? That is e to the negative x divided by the derivative of negative x, which is negative 1. So you put a little minus there. And yeah, what else? Blah, blah, blah. Okay, so apply the integration by parts, uv minus v du. So u is x, v is negative e to the negative x minus the integral v du. So v is negative e to the negative x, and du is 1 dx, right? The integral of u, the derivative of u is 1 dx. So your du, so it's minus v du. So du is dx. So you just add dx. So you can kind of clean this up. So let's see. Over here, you have a minus, and then you have a minus now that becomes positive. So it's e to the negative x dx. What is the integral of e to the negative x dx? It is e to the negative x divided by the derivative of negative x, which is negative 1. What's x times negative e to the negative x? It is, I guess you can rewrite that as negative x e to the negative x. And then you have this extra minus, so it's minus e to the negative x. Okay, so, and then over here, the integral of e to the negative x was negative e to the negative x. So now we can rewrite this. So now we can rewrite our problem as the limit as b goes to infinity of negative e to the negative x. Oh, I'm missing something. I have to, there is a minus right in the middle, right? There's a minus right in the middle. Yeah. So don't forget about that extra minus. That is going to be, yeah, you have a minus. So distribute this minus. So that's going to be positive x e to the negative x plus e to the negative x. And then we can do the rule 1. So our lower boundary is 1 and our upper boundary is b. Now, before you apply our lower and upper boundary, do you see anything that cancels? Yes, I see this e to the negative x and this negative e to the x canceling. You're gonna, so now this simplifies as the limit as b goes to infinity from x e to the negative x from 1 to b. Now you can do the fundamental, you can write it as two separate limits. So it would be the limit as b goes to infinity of b e to the negative b minus the limit as b goes to infinity of 1 e to the negative 1. So it's going to be the limit as b goes to infinity, and then it's going to be b over e to the b. So what's e to the negative b? That can be written as 1 over e to the b minus the limit as b goes to infinity, and then e to the negative 1 is the same thing as 1 over e. Okay, so now apply the fundamental. So we're still going from infinity. So over here, you're going to replace b with infinity. So that's going to be infinity over e to the infinity minus be careful. This 1 over e, there's no letters. 1 over e is a constant. So what is the limit as b approaches infinity of a constant? It's just that constant. So this is going to be 1 over e. Okay, now we kind of have a problem right here. Infinity over e to the infinity. How do we do that? Uh, yeah, it's an indeterminate, so you can must use L'Hopital's rule. You can use L'Hopital's rule. So it's going to be the limit as b goes to infinity. And then I'm going to rewrite this as, so you take L'Hopital's rule. Basically, you take the derivative of the numerator and the denominator until you don't get an indeterminate form. So what's the derivative of b? 1. What's the derivative e to the b? E to the b. And then this stays the same. So now does this work? So what is the limit as b approaches infinity? This is 1 over e to infinity minus 1 over e. So what's 1 over e? What is 1 over e to infinity? That's 0 minus 1 over e. So your final answer is negative 1 over e. Okay, let's move on to example 7. Example 7, we have our boundaries from negative infinity to positive infinity of x dx. So the integral of x dx is not too bad, but what is the rule if our boundary are both infinity? So one is a negative infinity, and then the upper boundary is positive infinity, so that would be rule 3, right? That would be rule 3. So we're going to rewrite this problem as from negative infinity to 0 of x dx plus the integral from 0 to infinity of x dx. So before we move on, what is the integral of x dx? This has a power of 1, so that's going to be 1/2 x squared. Or you could say x squared over 2, same thing. So this is going to be the limit as, you can rewrite this as the limit as a approaches negative infinity. And then we said that the integral of x dx is x squared over 2 from a to 0 plus the limit as b approaches infinity. And then we know that the integral of x is also x squared over 2 from 0 to b. Okay, now you may apply the fundamental. So this is going to be the limit as a approaches negative infinity. And then apply upper minus lower. So it's going to be 0 squared over 2 minus a squared over 2 plus the limit as b approaches infinity. Then over here, apply the upper minus lower. So it's going to be b squared over 2 minus 0 squared over 2. So this is going to be the limit as a approaches negative infinity. And then 0 squared over 2 is 0 minus a squared over 2 is just itself negative a squared over 2 plus the limit as b approaches infinity. B squared over 2 stays the same. Minus 0 squared over 2 is 0, so you don't need that. Okay, then you apply your boundary. So over here, what is the limit as a approaches negative infinity of this? So it's going to be minus, and then replace a with negative infinity, square over 2, plus over here, what is the limit? What is the limit as b approaches infinity of b squared over 2? So that is going to be infinity square over 2. So negative infinity square is positive infinity, and then you have this extra minus, so that's negative infinity over 2, plus infinity square is infinity over 2. Uh, what's negative infinity over 2? That's still technically negative infinity. Plus, what's infinity over 2? That's still technically positive infinity. So what is negative infinity plus infinity? And do not say 0, it's not 0. So it's a very small number plus a very large number. We have no idea because this could be like negative 1.6 million, right? And then this could be 100 billion, right? We don't know. So we have no idea. We have no idea what infinity is. So it's going to be diverge. But negative infinity plus infinity does not equal 0. We just don't know what this really small number is, and we don't know what this very large number is. Move on to example 8. Example 8, we have the boundaries from negative infinity to positive infinity of 1 over 4 plus x squared dx. So it's just like the example 7, our boundary is from negative infinity to positive. So um, let's break it into two separate intervals and make halfway point. Okay, so that's what I'm going to do. So we'll write it as two separate integrals. So this would be negative infinity to 0 because that's the rule of 1 plus 4 plus x squared dx plus the integrals from 0 to infinity of 1 over 4 plus x squared dx. So now, well, before going further, what is the integral of 1 over 4 plus x squared dx? It looks like the arc tangent, right? It's very similar to this. 1 over b squared plus ax squared dx. So that's the arctangent, which is 1 over ab times tan inverse of ax over b. So what would be our b? My b would be what number squared gives you 4? That would, oh, what number squared gives you 4? That would be 2. And what would be a? What number squared? This has an invisible 1. So what number squared gives you 1? 1. So my b is 2 and my a is 1. So that is going to be 1 over AB. A is 1, B is 2, times the tan inverse of ax over b. A is 1, x, and b is 2. Okay. So I guess this is going to be 1 over 2 tan inverse of x over 2. Okay. So we can rewrite our problem as the limit as a approaches negative infinity 1 over 2 tan inverse of x over 2 from a to 0 plus, because we wrote out as 2 separate integrals, plus the limit as b goes to infinity of 1 over 1 times 2 times the tan inverse of x over 2. But then this boundary is from 0 to b. Okay, so we can rewrite this as the limit as a approaches negative infinity of 1/2 inverse x over 2, a to 0. It's the limit. I'm just rewriting it to make it look nicer. Plus limit as b goes to infinity of 1/2 tan inverse of x over 2, 0 to b. Okay, so now you can start plugging fundamental theorems. So this is going to be the limit as a approaches negative infinity of 1/2 tan inverse, and then do the upper minus lower. So it's going to be 0 over 2 minus 1/2 tan inverse of a over 2 plus the limit as b approaches infinity. And then this is going to be 1/2 tan inverse of b over 2 minus 1/2 tan inverse of 0 over 2. Okay, so right here, this is where we stopped. So tan inverse 0 over 2 is 1/2 tan inverse 0 over 2 is 0, right? Minus 1/2 of tan inverse of a over 2 plus the limit of plus limit of blah 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 as b approaches infinity of 1/2 tan inverse of b over 2 minus 1/2 tan inverse of 0. Okay. Okay, so spin this up. So this is just going to be 0. Tan inverse of 0 is 0. Yeah, so we know that tan inverse of 0. Tan inverse of 0. What degree gives you tangent of 0? 0. Okay, so this is 0, so now you're left with this. So you're going to rewrite it as limit as a approaches negative infinity of negative 1/2 tan inverse of a over 2. That's the limit. And as v approaches infinity, of 1/2 tan inverse of b over 2 minus 1/2 tan inverse of negative infinity over 2 plus half tan inverse of infinity over 2 minus 1/2 tan inverse of negative infinity plus 1/2 tan inverse of infinity. And if you recall, what is the graph of a tan inverse? It is we would do something like this. Okay, so this is going to help with this. So right, so if we kind of go up here, if you look, what is negative 1/2 tan inverse of, and then a is negative infinity. So as a goes to negative infinity, the y value. So if you look at the tan inverse graph, as a goes to negative infinity, uh, the y value is negative pi halves. So it's going to be negative 1/2 times negative pi halves. And then if you look up here, so this is going to be negative 1/2 times, uh, so wait, right here, this is going to be negative 1/2, and then the tan inverse of negative infinity is negative pi over 2, plus over here, what's 1/2? That's going to be 1/2. What's the tan inverse as b goes infinity? If you look at the tan inverse, as b goes to infinity, the y value is positive 1/2. So it's going to be positive 1/2 times pi over 2, right? If you look at the tan inverse, as you go more to the right, the y value shoots up to positive pi halves. And I think these all cancels out. So really, you're really just left with negative 1/2 times negative pi over 2 plus half times positive pi over 2. So over here, negative 1/2 times negative 1/2 times negative pi over 2 is positive pi over 4 plus 1/2 times pi over 2 is pi over 4. So pi over 4 plus pi over 4 is 2 pi over 4. Then we know it converges, and then it converges to pi over 2, right? Because 2 pi over 4 reduces by 2. So yeah, pi over 2. Um, our next problems are we're going to deal with some kind of discontinuity. Discontinuity. Let's move on to example 9. Okay, example 9 says we have to take the integrals from 0 to 1 of 1 over x dx. So is this even improper? No, this is not improper, right? So we're not going to use, yeah, we're not going to use our special improper integral rules. I wanted to go over this one because it's dealing with discontinuity. So x can be any number besides 0 and x. So x, you know what a 1 over x graph looks like. It looks like this. Got it. Here's your x. Here's a y. Vertical asymptote, horizontal, and then it looks like this. So you know that x can be any real number besides 0. So x cannot equal to 0, but you can approach 0. And we are going to approach 0 on the right side. So we can rewrite this as the limit as a approaches 0 to the right from the integrals of 1 over a 1 over x dx. And then we could say the limit as a approaches 0 to the right of ln of absolute value of x from a to 1. So that can be written as limit as a approaches 0 to the right of ln of absolute value 1 minus the limit as a approaches 0 to the right of ln of absolute value of a. Okay, so it's going to be the limit as a approaches 0 to the right. And then ln of 1 is 0 if you put that in the calculator, minus the limit as a approaches 0 to the right of ln of absolute value of a. So this is going to be 0 minus, what is this going to be? So if you recall, what does the natural log graph looks like? It looks like this. Has an x-intercept of 1 comma 0, and then it slowly starts to decrease like this. So as the limit as a approaches 0 to the right, so it's going to be minus the limit as a approaches 0 to the right, ln of the absolute value of a. It's going to be 0 minus 0. Here's x value 0. So what is the limit as a approaches 0 to the right? It shoots down to negative infinity, right? So it's going to be negative infinity. So yeah, so it's going to be infinite. So two negatives becomes a positive, so 0 plus infinity. So you could say infinity or undefined. You can also say it diverge. Okay, let's move on to example 10. Okay, example 10, we have the integrals from 0 to 1 of 1 over the cube root of x squared dx. So what can your x be? So your x can be anything but 0, right? So if you plug in 0, you have undefined, right? So this is why we have to redo this problem. So your x value can be any number except never 0. And unfortunately, if you look at our limit, our y value on our limit, our lower boundary is 0. So that means we can approach it, but can't touch it. We are going to approach 0 on the right-hand side. Okay, so we're going to say the limit as a approaches 0 to the right from the integrals 1 to a, 1 over the cube root of x squared dx. And then we're going to rewrite it as the limit as a approaches 0 to the right. And let's rewrite, this is going to still be a to 1. Let's rewrite 1 over the cube root of x squared as a power. So it'd be 1 over x 2/3 dx. And then let's rewrite 1 over x 2/3 as a negative power. Let's find the integral of this. What is the integral for 1 over x to the 2/3 dx? Well, I'm going to rewrite this as a negative power, so this is going to be x to the negative 2/3 dx. And you know how to take the integral of this. It's just whole power plus 1 divided by that power, so it's going to be x to the negative 2/3 plus 3 over 3 over negative 2/3 plus 3 over 3 is 1/3. So this is going to be x, and then negative 2/3 plus 3 over 3 is 1/3 divided by 1/3. And you have a improper integral, so this is going to be 3x to the 1/3 over 1. So yeah, you're going to rewrite this as the limit as a approaches 0 to the right of 3x to the 1/3 from a to 1. And then do the upper minus lower. So you're going to say limit as a approaches 0 to the right of 3 to the 1 raised to the 1/3 minus the limit as a approaches 0 to the right of 3 times a to the 1/3. So it's going to be the limit as a approaches 0 to the right, and then 1 raised to the 1/3 times 3 is 3, minus the limit as a approaches 0 to the right of 3 cube root of a. And if you recall, what is the cube root of x? The y equals cube root of x graph looks like. It looks like this. Okay, it would look something like this. Okay, so as a limit, as a approaches 0 to the right, 0 to the right, the y value still is 0. So it's going to be 3 minus 0, just 3. Let's move on. Okay, let's move on to example 11. what is the integral from -1 to 2 of this rational function 1 over x squared dx? So you obviously have a problem if you plug in -1 in the lower boundary, right? 1 over -1 square. Uh, oh wait, that's fine. But the only what makes it undefined is when you plug in. So you cannot plug in x equals 0. But look at your boundaries. Our boundary is from -1 to 2. So 0 is between -1 and 2, right? So we have some kind of discontinuity. So you cannot plug x equals 0, but 0 is between the intervals -1 to 2. So if you really want to graph it, it would look something like this. Um, this rational function would look like this. Uh, Here that 2. And we're only going from -1 to 2, so this is this area. And then here's -1. It would look something like this. Oops, sorry, we're only going from -1. You don't need this area, not this. So you have, as you can see, you have a vertical asymptote right in the middle at x equals 0. So that's why you can't really include 0. So it's discontinuous at x equals 0. If you look at the line chart from -1 to 0, and then from 0 to 2, let's see here. So this is going to be expressed as oops. So you're going to rewrite this as two separate integrals. You can say the limit as b goes to 0 to the left of the integrals. We're going to break it into two separate integrals from -1 to b of 1 over x dx plus the limit as a approaches 0 to the right from the integral a to 2, 1 over x dx. So it's going to be the limit as b approaches 0 to the left from -1 to b. And let's rewrite 1 over x squared as, no, wait, what's the integral of 1 over x squared dx? Let's rewrite it as x to the -2 dx. And then that would be whole power plus 1, so -2 plus 1 is -1. Over -1, so that is negative x to the -1, which is negative 1 over x. Okay, so now we know that, so we're going to rewrite this as the limit as b approaches 0 to the left of negative 1 over x from negative 1 to b plus the limit as a approaches 0 to the right of negative 1 over x from a to 2. Okay, so it's going to be limit as b approaches 0 to the left, and then apply the fundamental. So this is going to be negative 1 over b minus bracket negative 1 over negative 1, right? For this fundamental. And then do the fundamental for this one. So it's going to be the limit as a approaches 0 to the right. It's going to be negative 1 over 2 minus negative 1 over a. So it's going to be the limit as b approaches 0 to the left of negative 1 over b. And then two negatives becomes a positive, and then you have this extra minus, so it's minus 1 plus the limit as a approaches 0 to the right. And then this is going to be negative 1/2. Over here, two negatives becomes a positive, so that's 1 over a. And let's figure out, okay, so we have two graphs. We have 1 over a and negative 1 over b. So what are these two graphs looks like? So y equals negative 1 over x graph looks like this. It's a rational. You have a vertical asymptote. You have vertical and a horizontal asymptote at 0. It looks something like this. Okay, so when you plug in, what is it? Infinity. So as you go 0 to the positive, 0 to the right, the y value shoots up to positive infinity. And then you still have this minus 1 plus negative 1/2. And then what is the limit as 0 goes to the, so this is this graph. Now what about this graph? Y equals 1 over x. That graph looks like this. It looks like this. So yeah, as 0 goes to the right, the y value shoots up to positive infinity. Okay, so 0 minus 1 is still infinity, plus negative 1/2 plus infinity is still infinity. What's infinity plus infinity? It's infinity. Or you could say undefined or diverge. Uh, let's move on to 12 then. I think there's only two more problems. 12. So on 12, we have the integrals from 0 to 3 of dx over x minus 1 raised to the 2/3. So we definitely have some kind of discontinuity. I believe you have this is a rational function. And then you also have a vertical asymptote. And you have a horizontal asymptote. So how do you find the vertical asymptote? You basically set the denominator to 0 and solve for x, right? So our denominator is x minus 1 raised to the 2/3. You set that to 0, and then you try to solve for x. So what I would do next is get rid of the power of 2/3 by raising everything to the 3/2. It's x minus 1, this powers disappear, so you're left with 0 raised to the 3/2, which is 0, and then you add 1. So your vertical asymptote is at x equals 1. So you have a discontinuity there. The thing is, our boundary is from 0 to 3. Yeah, 0 to 3 is definitely between, 1 is definitely between 0 and 3, right? Yeah, 1 is definitely between 0 and 3. So we're going to write out, we have a discontinuity there, so we're going to write it out as two separate limits. We could say the limit as b approaches 1 to the left from the integrals 0 to b of x minus 1 raised to the negative 2/3. Wait, what is the integral? So let's do that real quick. What is the integral of x minus 1 raised to the negative 2/3? What would that be? Well, let's just write it out first. And then the other one would be the limit as a approaches 1 to the right, and the integral a to 3 of x minus 1 to the negative 2/3 dx. So I guess you could do some kind of u substitution, right? Yeah, the integral of x minus 1 to the negative 2/3 dx, you can definitely do some kind of u substitution. Your u would be x minus 1, your du would be 1 dx, that's nice. So it's going to be u to the negative 2/3 dx. And then what's the integral of u to the negative 2/3 dx? It is 3u to the 1/3, or 3 parentheses x minus 1 to the 1/3. Okay, so we could say we'll write out our two limits. So it's going to be the limit as b goes to 1 to the left of 3u to the 1/3 plus the limit as a approaches 1 to the right of 3u to the 1/3. Okay, and then apply your fundamental. The limit as b goes to 1 to the left of 3, replace x with x minus 1 to the 1/3 from 0 to b plus the limit as a approaches 1 to the right of 3 parentheses x minus 1 to the 1/3, a to 3. And then plus the limit as a approaches 1 to the right of 3 cube. 1/3 is the same thing as cube root. And then it's going to be 3 minus 1. Or no, it's b minus, if we do the b minus 1 minus, so I'm applying the fundamental theorem for this part right here, minus 3 cube root, because 1/3 is the same thing as cube root, 0 minus 1 plus the limit as a approaches 1 to the right, 3 cube root, and then it's going to be 3 minus 1 minus 3 cube root of a minus 1. You clean it up, it's going to be the limit as b goes to 1 to the left of 3 cube root of b minus 1 plus 3 plus the limit as a approaches 1 to the right of 3 cube root of 2 minus 3 cube root of a minus 1. So this right here, that's going to be 0. Right, when you plug in 1 for a, that's going to be 0. So now you're left with y equals 3 cube root of x minus 1. So what does that look like? Well, what does a regular cube root of x graph look like? It looks like this. What about the graph y equals 3 cube root of x minus 1? That has a horizontal shift of 1. And it's going to look like this. So it's going to be 0. Yeah, it's going to be, our final answer is going to be, when you plug in your limits, it's going to be 0 plus 3 plus 3 cube root of 2 minus 0. So that's going to be 0 plus 3 is 3 plus 3 cube root 2. Okay, we'll just stop here. This will be the last problem. So yeah,